Excuse me. Good evening. Turn it up, maybe? Yeah. Testing. Oh, perfect. Okay. That's better. Good evening. How's the volume? Everybody okay? Too loud? Anything? Okay. Good deal. I'm Angela Metler. I'm an administrative assistant in the president's office at South Dakota Mines. Welcome to STEAM Café. Thank you so much for coming. STEAM Café is a partnership with Camp Brewing and South Dakota Public Broadcasting. We couldn't do it without them, and we couldn't do it without you. So I want to thank everybody who's here today. It looks like mic issues, maybe? Maybe? Can you hear me? Maybe I'll just yell. I don't think so. So we do this every third Tuesday, and tonight's presenter is Caleb Ziolkowski from the Crazy Horse Memorial Foundation. So without further ado, our presenter.
Testing 1, 2, testing. Oh, there's a green light. Oh yeah, there's noise, volume. Is that a good level? No. I turn it off again, turn it off and back on. Mic check, testing 1, 2, testing, testing. Okay, we've got some thumbs up. I'm hearing a little ring, but I'll just push on if that works. First, thanks to Jade Herman inviting me here. When you get an invitation from someone whose title is Chief of Staff of the President, you're like, I better do that. And so I'm doing that. I work up at Crazy Horse Memorial, and I have the pleasure of talking to you tonight about that project. And Jade, when she was saying, oh, Caleb, Crazy Horse would be perfect for this, she's like, this is STEAM Café, and you have all of STEAM going on at Crazy Horse. And I was like, testing one, we're going in and out, aren't we? Okay. But I was like, you're right. The only problem is the messenger. There might be a few issues with me. I'm a political scientist. Like, I know that's the softest of sciences, right? And technology, sometimes I'm able to work with it. I have no idea what's going on under the hood. Engineering, don't get me started. Engineers, you're too smart. I can't do it, all right? Art, I'm probably in charge of the world's largest piece of art, right up there. I'm not an artist. Math, well, I've got a bit of a background in statistics, but like anyone who really cares about math, there's like, that is an aberration. Like, you're focused on uncertainty. Like, the nice thing about math is you get exact answers and it's black and white. So with all that said, hopefully we can still find something worthwhile to say in spite of my shortcomings. Best slide, quick disclaimer, all these images are copyrighted and the opinions expressed, no matter how poorly, are my own. Also, something very important to state up front, the scope of this project, its history, both in terms of its physicality, temporally, the really skilled people who have worked on it for many years more than I have. There's just too much for me to cover. We actually have, I don't know where he went off to, but Jim McNulty here, he's worked here for a long time. I promised him if there's some really difficult questions that come up, I'm just gonna put him on the spot and make him answer them. And so without apologies, I'm going to focus mostly on some of the parts I know best, but also give a brief overview of sort of how I see STEAM being present at Crazy Horse. The A, I don't think I really have to argue that this is art. And yet, I think it would be salubrious for us to ruminate on what that entails. I worked for a long time on that sentence. And one thing that I like to draw on is a lot of important Native American leaders saw a crucial role for art. And Luis Real of the Métis, just one example, said, "My people will sleep for 100 years, but when they awake, it will be the artists that give them their spirit back." I think this is tapping into something that many of us know. Art has an ability to move us profoundly. And in the words of Louis Ratis, it can do something to give us our spirit back. It's not just any form of art, it's a specific type of art, it's sculpture. I like what Anthony Gromley says, a sculpture is this thing that has the capability of changing your mind, altering the way you feel, inviting you to look at the world in a completely different way. It's a material proposition, which asks, can we look at the world like this? And I think in the case of Crazy Horse, we really have a piece of art where the founders, the original sculptor, my grandfather, Chief Henry Standing Bear, this is what they had in mind. This is an object that exists out there in the world, in a very specific place in the world, and it's meant to challenge, to confront people when they see it. Who is this person? Why is this memorial dedicated to him? Lastly, in terms of art, it's on an incredible scale. This is from earlier this summer at the Volksmarch. And well, I love this picture, one, because the little dots, those are people. And so it really does show that this is on a massive scale. To throw some numbers at you, that hand that we were able to unveil at the 75th anniversary, about 871.92 cubic yards. I think it's close to 3 million pounds, roughly the weight of 892 mid-sized cars. And that's the hand. Between the hand and the face, again, in this picture, they're very impressive, but the surface area of what we finished or have nearly finished is right around 3% of the projected surface area of the entire mountain. It's breathtaking if you stand up in front of Crazy Horse's face, but then you have to remember this is in some ways less than the tip of the iceberg. Also, this scale requires the rest of these disciplines that we're talking about, the rest of STEAM. Again, disclaimer, I'm not an engineer, but I understand there's this engineering design process. And I also understand that there's some flexibility as to what exactly the different phases in this process are. And as I was reading about it, I was like, this is actually a really good way to understand just the project on a big scale and then also specific challenges we face. The problem, carve a mountain, right? A very big mountain at that. Specific requirements, there's more than listed here, but there needs to be a certain degree of control and fidelity in that process, fidelity to the model. I think it's really important to recognize just how constrained resources can be, have been at times. I love this photo. I should say specific requirement has sometimes included more of an emphasis on safety than others. So that's my Uncle Mark, no hard hat. And then my dad, he told me the other day he remembers like putting his arm in front of his face to try to stop the dust and the drill bits coming up and hitting him in the face, the bits of rock. And so constrained resources, like ideally you'd have an adult running a pneumatic rock drill. And then when you set out, like, okay, we need to carve this, where can we get some ideas from? There's a fairly small epistemic community when it comes to mountain carving, and we've borrowed heavily from that. A lot of the things that we've started with from Mount Rushmore, and then you go to other related or tangential industries to try to find things that you can use. You brainstorm, okay, we've got these different options we found. What seems like it'd work best? Let's test those. Let's analyze the results, iterate, try to keep improving our process. And then I also like to think about it in terms of more specific challenges, this whole enterprise of rock carving or mountain carving. One is what I call this location challenge. And it's almost as simple as you get up on that mountain and you're like, okay, now where exactly am I on this mountain? Yeah, we've got a model and we've got a mountain. What's the translation between the two? How do I know, is this the rock I need to remove? What about 3 inches further this way? What about 10 inches further this way? And the initial answer to this is Korchak, my grandfather, was like, that's the rock we remove, right? He's an artist. He looks at the model, he steps back, he looks at the rock, he's like, that needs to go. He wasn't around forever. And when they went to work on the face, they pulled something directly from the Mount Rushmore playbook, which is we're going to have a scale model, 1/34 the size. We put a pointing machine on top of it with an origin point, and then you can measure your angle, your distance from that origin point, and your elevation to a desired point you'd like to know the location on that scale model. And then you just scale up those latter 2 measurements by 34. And I think they pointed something like 10,000 points by this means over the decade or so working on that face. So pretty incredible. Another challenge that you have to deal with is what I'll call the bulk rock challenge. You decide that you need to remove a good amount of rock. How do you do it? And for a very long time, the answer was high-grade explosives, very efficient means of moving rock when you need to. And this process grew more technical and more controlled and more sophisticated as the project went on. Another key challenge is, okay, now you've gotten really close. How do you finish these details? You can point it out with the pointing machine, you know you need to remove some rock, but how do you actually shape that in a controlled way? A big answer was and continues to be torch, diesel jet torch. And it gives a really nice, smooth flame finish. Borrowed that from the dimensional stone industry. And like I said, we're still using that today. The results, I apologize for the blurriness of some of the photos because they really are breathtaking. There's going to be certain slides in the near future which will be far less breathtaking. So I apologize we're not getting to really see how amazing these are. This is some of the technicality of the blasting that they did on the face with the splits. Like, people from the blasting industry were traveling near and far, nationally, internationally, to see the work that they were doing. It's really incredible. And I think there's the second sense in which it's really incredible. People, casual observers, maybe not so casual observers, saw this mountain changing over 40, 50 years. And they're like, I can tell the shape is changing, but I'm not really sure I can see what's going on. I'm not sure I catch the vision. And then I think once that face is finished, it becomes a lot easier for people to see the vision when it's staring back at them, right? And again, incredible work. I think we were really hitting an amazing stride. We very efficiently moved a lot of rock on the front of the mountain. I believe over 1 million tons over the last 25 years, a lot of it happening in the 15 years after the face was finished in 1998. And so here you see far less rock than there was before. But of course, life's never as simple as keep on doing what's been working. We got sort of a bulk rock removal challenge curveball. When we got out to the hand, engineering consultants, they looked at the features, did some geotechnical analysis. They looked at the finished shape of the carving and they said, we're going to advise that you don't use explosives out here if you can avoid it. And it's like, again, the crew, they know how to use explosives. This is like their specialty. So how do you learn a new way to address this challenge? Well, one thing that we researched, brought in, tried out, shimming and wedging. In terms of resources, it's pretty simple to buy some shims and some wedges. We started out with just like 16, 18-pound sledgehammers and just like go for it. But in another sense, it's like actually very brutal in terms of the labor demands it makes on you. Another tool we found from the dimensional stone industry, diamond cable saws. And we'll, again, we'll zoom in here. It's gonna all be blurry, but essentially you have a flywheel that you can somehow put tension on. And if you can wrap this diamond cable around some rock, put that tension on it, rotate it, add some water for dust control and also to keep the heat down, you can cut through like rock fairly efficiently. It takes a little time, but you can do it in a very, very controlled way as well. And so we're figuring out how to do this, but the real trick is a lot of times the rock that you want to remove, you cannot simply wrap the cable around it, right? There's other rock around it. There's rock you want to leave in place while you remove some of the rock. And so you need to start drilling these holes. And these holes have to be quite precise. Imagine if you're drilling something like a 10-foot hole, a 5-foot hole, a 6-foot hole from very specific angles. And you're doing something like 1 3/8. The smaller you can drill these, really the better, because then you're going to keep your planes that you're cutting with these diamond cable saws closer to the rock that is finished grade. And it doesn't take much to miss from 10 feet away with a 1 3/8 bit. And another thing we've had to learn to do is how do we drill really precise holes? Something that has, oh man, graphs. Graphs are fun. We have been getting better and better at removing rock. Even though the lines are blurry, this is just y-axis, amount of rock removed, tons. X-axis is measuring up sort of from the beginning of the summer to the end of the year. These first two lower lines, they're very low, about 6 times lower than sort of this big thick line. That's when we were just shimming and wedging, very brutal. But over time, as we've been phasing in cable saws, I think we've seen a nice uptick in how quickly we're removing rock. And we did get better with the shims and wedges too, but at this point, I think we're all on board with if we can use a cable saw, let's do that. Another important thing, this is an example of a larger trend, is technology is changing. We had the shot of the pointing machine before. Now we've got really incredible modern surveying techniques. This is actually a GNSS rover. We've got terrestrial surveying equipment too. And we even just recently got I want to say drone. What's the right term? UAS, unmanned aerial system, LiDAR scanner, which that thing's incredible in the sense that you can scan the entire mountain in 15 minutes. Jim, you and I spent, I think, 2 weeks, 3 weeks one summer getting a very patchy scan of some of the top of the head. So it's like night and day how technology can change certain things, including being able to drill really accurate holes. So that has played an important part in some of this process of drilling accurate holes. Planning these saw cuts, perhaps unsurprisingly, we're using computers a lot and designing those things. I warned you the graphics were going to get worse. Like these are just things that I threw together on my computer today. But this is, we'll still try to go through this, the top of the index finger, the tip of it, and then we have horse's mane running right under there. Maybe you'll be able to get a little bit of a picture for that. Oh, this is going to be where we run into real problems. Okay, so this is a scan of the model itself, and so we'll just try to rotate it. You'll get a little bit of an idea. There's mane underneath that index finger. We're using a working model, and Korchak said this before he passed. He's like, you can only carve what the mountain will let you carve. And so we take that very seriously. And one of the things that means is we don't like to have huge overhangs. You could imagine that finger hanging out there in space. That's a lot of weight. It would probably stay for quite a while. You could maybe get it to stay for 200 years, but we have bigger plans, 5,000 years. That's the kind of timeline we're hoping for. So we do modify it as seems appropriate to satisfy that goal of letting this stand not just for a couple centuries, but for several millennia. And we'll see. I've been told that I have way too many slides, and so the computer struggles to buffer it as well. This is just rotating that rock again. So this is a scan of the mountain. So you can kind of already see how computers are very useful tools in planning where to remove rock. This is the chunk of rock that we're gonna focus in on. I planned a saw cut there, and we had, I think 5 holes we drilled, and we just had that amazing graph of rock removal records. It's like, how do you know exactly how much rock you removed? So here, I'll jump into the weeds a little bit. Initially, we were saying, well, this block that we're cutting, and these blocks are getting to be weirder and weirder shapes all the time, but we're like, this block that we're cutting, it's kind of, like this shape that we have a formula for, and this other shape we have a formula for, and this little part is like this shape. Sometimes they're pretty rectangular, prism-like, and the formulas. You can figure out if you measure the dimensions, the volume and then the weight. But like this sort of block here, it's pretty weird. I don't know if you can really tell, but just if you can't see it, imagine a weird shape. And one really exciting, this is where I'm gonna just nerd out way too much. Exciting thing you can do in this type of situation is use a Monte Carlo estimation to figure out the volume. And I like this not because it's state-of-the-art Monte Carlo, but because it's just such a pure application of Monte Carlo for numerical integration. So you can imagine just using some Boolean logic with these planes that we're cutting that we've already planned. And I'll use just a flexible general additive model on the front to basically make a statement like, is this point in space inside the rock that's being removed, or is it outside of it? And then for our sampling space, we can just make a box, a rectangular prism that's a little bit larger than the rock that we're taking off. And it happens to be the case that we know the formula for the volume of a rectangular prism. We don't know the formula for this weird shape, but what we can do is put a bunch of points out there at random, right? Using uniform distributions, like I'm getting my statistics in here now. Using uniform distributions to say, this is the lower upper bound on all 3 dimensions. We're going to randomly generate points, evaluate, is that point within the rock that we're taking off or outside of it? We do this a lot of times, right? The pink dots are not inside, that yellow one is inside. You just keep picking these points at random. You do this like 2 million times, right? The computer does it 2 million times. You just click go. And look at that visual, right? Very good. Okay, so if we take away the points that are not inside the rock, this is what the computer thinks are these points inside the rock, given that Boolean logic. If you can't see it, just imagine these points fitting really well in this weird shape. And then it's pretty straightforward after that. You just have your volume of your sample space. You multiply that by the number of points in the in the rock that you're taking off, divided by the 2 million that you've drawn, or however many, and you get your number of volume. You can translate that to tons. So this piece, it was not big, 1.03 tons or so. And the nice thing about that is, well, the nice thing about algorithms and computer programming in general, if you can get it right once, except for edge cases, you can just let it go. And so at this point, none of us on the crew have to sit down and say, what shape does that look like? What combination of shapes does that look like? How can we figure out that volume? All right. I don't know how I'm doing for time. I'm great, yeah. All right. It's also interesting, we're kind of in this ecosystem where technology enters one part of the process, changes how you approach that, and then it opens up new options further down the line. So we had the detail carving challenge. Well, with new things happening with how we're removing bulk rock, these saw cuts were able to really approximate fairly closely what is finished grade, but we're doing so in sort of a sculpture by Picasso way, right? A bunch of planes, because those planes are what we can cut with a lot of control. You can try to curve a cable saw cut, but where the tail of that cable is going to run through, it's kind of a guessing game. So if you cut planes, you're in good shape. You can start to approximate round surfaces by cutting a lot of planes, but at some point there's diminishing returns to how much you're going to do that. But you are, in many cases, within 3/6 of a foot from finished grade after you've done these cable saw cuts. So you're pretty close. And I don't know, I think a couple of our fabricators, machinists had this crazy idea, right? We've already sort of hinted at this. There's not a huge market out there for mountain carving equipment, but they do make things like Husqvarna makes this rail saw. It's a little hard to see, but it's a rotating blade. It's on a radial arm and it travels along a rail, right? And it can cut through rock quite efficiently, but if you got this depth adjustment and you can move horizontally, you only have 2 dimensions. And these machinists, they want 3 dimensions. They're like, we could have 3 dimensions of movement. And so just to orient us, because we're going to come back to this a little, we're right on the tip of the thumb, really the top half of the thumb and the front of it. And what they decided was like, okay, we've got those 2 movements. Let's give it a third. Let's put the whole rail saw on a set of rails. And then let's bolt it to the rock. And now we just need to figure out at each location, sort of on this grid of horizontal and vertical movements, how deep do we need that blade to go? And the second thing is, well, the way to address this issue, we get a survey instrument and you say, okay, where is this thing at? We like to shoot 4 corners, and that gives us our vectors. And it also goes across the whole range that we're working. So I feel like we're pretty confident usually in the location of this thing. And you take those that you shoot out in the physical world, you get them into our local coordinate system, and then you can come digitally and say like, oh, this is where you're at relative to the model that we're working towards. So then you're like, okay, this is the first row we're cutting. How do we know exactly how far that blade should go? And to try to give you a little idea, I've just highlighted in red a portion of the finished grade of the scanned points from that model that represent that plane, well, where the plane that blade is moving in will intersect the model. And this is going to be where this really goes off the rails, because I think I was like, I've got a brilliant idea. I'm going to keep this very simple. I'll just have images. And this point is supposed to be basically a video, but I was like, I'll just click through really fast, but I think the computer might have problems with that. You figure out where that center of that arm is. You just keep moving it in. until I'm just gonna go for it. We'll see how, I was challenged to try to break this. But you write a piece of computer code. It's a pretty simple algorithm with a while statement and some if statements, and just like keep moving until you get to a certain distance from those points of concern, maybe about an inch. And once you've gotten there, you get into another fairly simple while statement that's like saying, okay, are you okay at this position? Do you need to move out some? Can you go in some? And you just keep moving across as you do that. And so you get basically the location of at every, well, we're making it discrete, so every 1/10 of a foot, how far do you need to be with that blade? And I think we're solving here for the actual XYZ coordinates, but we will then on the back end translate it to human numerical control, right? This was basically I described as CNC machine, but it's not CNC at this point. It's human numerical control, HNC. So a person will get a spreadsheet on a phone or something, and they'll say, okay, starting at height 1, rail position 0, you need to be at depth 7. And you continue that over to 1.2 feet on the rail, at which point you will move to depth 7.5 and so forth. Very monotonous. Obviously, it would be much nicer if it was computer numerical control. But all that being said, we're kind of back to the limited resources, like doing what we can with what we have. And the results in terms of post-cut surface, you can't really see in that photo. Here's a heat map of 4 of the cuts that we've done there. This area is the tip of the nail, and we're doing a little more. When you're doing a 1/60th model, there's only so much detail you can put on something like a thumbnail. So in the real thing, you actually get more detail on the scaled up version. But otherwise, the green basically means we're within a 1/10 of a foot. Yellow between 1 and 2/10 or so. The red on the edges, that's where your blade starts curving up away. Or here, you maybe start losing, because it's on the vertical straight rails. If the surface curves away from you, you start just stroking out. You can't reach the surface anymore. But on the micro scale, the results of this have been really quite good. On the macro scale, this is not an apples to apples comparison, because the face was like completely done in 10 years. And once we run the finishing saw, we often have more fine details to put in. But just to put in perspective how well that kind of worked, working on the face, the green line, we're running about 500 square feet per year. And it looked like after we got used to the cable saws and the shimming and wedging, over a couple years, we started doing quite a bit of torching, and we were running at about, again, 500 square feet per year. And then since we introduced those finishing saws, the surface area that we were able to cover with that was roughly 5,000. So I was tempted at this point to be like, and this is where science is. And I was going to be like, I will run a regression analysis and tell you that the introduction of finishing saws was indeed statistically significant. I was like, maybe I should even do a regression discontinuity design and just like, but it's like one of those where the interocular trauma test works, right? Like it just hits you between the eyes, and I don't need to demean science in that way. Right? Yeah, it's like, just look at it. We're always trying to keep learning from what we've done in the past, what we could do differently. We're making plans to go about automating a lot of this finishing saw process. We've actually got some cool designs drawn up. I think we've got at this point, so at least you have a button to move the rails up and down. I didn't tell you, they were like crank rails at the beginning. But while I've been harping on resources being limited, they're not fixed. And we've actually had a really exciting donation come in that will help us get a robotic arm, an industrial robotic arm. Yeah, oh, I know. We've got a board member up here, Roger Brewer, and he's excited about a donation. We all are, Roger. I'm ecstatic. But we're working with the difficult thing is not finding a manufacturer that thinks they could make a robotic arm that would work in your case. It's finding the integrator that can actually make it work. And I think we've found maybe the one integrator in the country, because I asked all the other ones and they were like, no, we can't put this robotic arm on the side of a mountain. Well, we found the one that said, yes, we can do it. And so in some ways, that means it doesn't make as much sense to put our resources into automating that finishing saw the rest of the way. I'm not a development officer, but this the donation that has come in is also helping to buy a very large tower crane, 1,000-meter-ton series. And there's a matching component, a 2-for-1 matching component. So if any of you are interested in helping with the work on the project, contact, I don't know, a board member or something. I won't know what to do if you contact me. So I said I wasn't going to do the cheap science thing. I think I'm a sucker for the big picture philosophy of science argument. Or I think, while I said it was a small epistemic community working on mountain carving, there is really a body of knowledge that exists. How do you actually do this? Maybe at some point, related fields will look to us for some ideas. I don't know. But at the very least, the next big mountain carving that comes along, I think at this point in our process, given the record keeping that we're doing, the data-driven decisions we're making, we'll have something to contribute to their efforts. And in this, we're really just tracking the, I guess, the scientific endeavor more broadly. It's always, we think we have a great theory on how we do things, but we're open to looking at new information, new perspectives, and going to the data and then moving forward, which I think is incredibly honorable. It's a great way to live your life and think about things. So I am very happy to be talking at the STEAM Café, because I think this is a noble endeavor overall. At the same time, the mission of Crazy Horse isn't really rooted in STEAM per se. I mean, I think it's rooted in ethics and certain beliefs about how lives can best be valued and recognized. And the fact that in our mission of preserving and protecting the cultures, traditions, and living heritage of Native Americans, we can use STEAM as a handmaiden to help us get there, I think says even more wonderful things about STEAM and just this general enterprise. And I'm very appreciative of being asked to speak. I think I'm probably close to my time limit, so I will stop talking now and open up the floor to questions. Again, any very difficult questions, I will refer to Mr. James McNulty. Oh yeah, sorry.
Softer rock in places, here about the structural integrity of the rock underneath the arm.
Right. Yeah, one of the great things about the question about opening up the arm is I think that we can wait for that decision till the very end. We have really good access to that area. But again, this is one of those where we value the long term over the immediate artistic effect that you might have from opening it up. From other people would know better exactly the quality of the rock as we go down, but I know that some of the older guys on the crew that did a lot of the blasting down there have said that if anything, in general, as you go lower, the rock is getting tighter, it's getting better. So I think all of that so far, the geotechnical analysis that has been done, points in the direction that we've got a very feasible model given our material. Of course, you can always encounter a pocket of, I don't know, well, sometimes we encounter pockets of mica schist just in areas where we'd prefer not to. And so that's one of those where you just take it as you come. And then my grandfather's, you got to just let the mountain tell you what you can and can't carve come in. And we'll, I guess we'll take those problems as they come up. But so far, I mean, we don't have, you mentioned Mount Rushmore. They had this kind of nice thing where if you have 4 heads that you're carving and you need to move one, the other 3 can just stay, right? We only can move things so much before you like are starting to say, that does not look right, right? The hand should not be down there. So I'm not saying it's harder than what Mount Rushmore did. You come to your own conclusions, but we do have that challenge. And so we have to really look to work to the maximum extent with the rock that we have and modify things in such a way that we're gonna, I guess in some ways, honor that material that we're working with. Yeah. Right. Yeah, we initially, if you look at the original 1/34th, well, the original 1/300th, it's at such a small scale that it's a little hard to tell, but there's definitely a lot more overhanging rock on that. And it was rotated and has more main coming up underneath it just for these concerns, like again, working with our engineering consultant saying, yeah, it would be best to have some support here and saying, okay, we're going to do that for the long haul. Anyone else? Yeah, way in the back. Yep, yeah, we're just gonna put in an all-nighter. Not a problem. Yeah, I think this question, the initial question, actually, it's a useful thing to keep in mind with that. If we come up to some issue, it could end up, you know, we need to think about this for a couple years, do a lot of analysis, get some rock support in place. It does, the hockey stick does augur well for the future as long as things keep sort of running smoothly. Will things run smoothly? I don't know. I hope so, right? It looks nice when we make progress. But again, I kind of like to frame the when will it be done question in the sense that I love it. I mean, I want it to be done. It matters for so many people, for their lives. Like for some people, it's highly meaningful that this great Lakota warrior leader is being carved, and they would love to see it done 3 decades ago. At the same time, we have all these discussions about, well, because it's so meaningful and we want it to last a long time and we want it to look like it needs to look, it has to take as long as it's going to take. And so we're continually balancing between we really want to make more and more progress and we really want to do it right. And I think that's just a tension inherent in the endeavor. Friday, we're going to be done Friday. Yeah. Yes, sir.
Along those lines, would you be able to give us a sense of if you had all the tools you have today when you're working on days, how much less time would it take you?
Yeah, well, in some ways it's really hard to answer because I think we learned so much of what we do is based on lessons that they've learned. And so there's also this, do they get to know all the lessons that we learned because they did what they did question. I think it could have, and then there's still, the other thing about the face is they were doing a lot of details, a lot of really important features. I think you can probably, they also, I think if anything, were more resource constrained than we've been. There were a lot of really difficult years in terms of this funding. If it weren't for, I mean, donations, yes, and then like the blasting industry doing a lot to donate, that would have been tough. It's a tough question. Maybe we have a few things that we could have helped them with, but for the time, what they did, I'm just still in awe of that whole process and then the outcome. It's if you get the chance to go up on the arm and just look at that face, like you should do it. It's one of those experiences you don't forget. Yeah. And then you next. I'm sorry, I keep skipping you.
Everything like is privately governance. I have the utmost admiration for it down because it's true grassroots. So, for everything that your family, foundation, and so first, just to put that out, everything that you've done is grassroots. The other question that I was going to ask is, what are you doing with the old road? Are you locating the purpose in any way? So what? You know, simply the second part.
The second part was, what do we do with the overburden? Like all of. Yeah, you're talking about all of this and this.
How exactly? Construction, street, road, aggregates that being examined for other minerals that may be available in that.
No, great questions, and thank you for the kudos. And I should point out we have multiple members of the board here this evening, so they also are a huge part of what we're able to do and stay true to our mission. I think they help keep us on track and always focused on the bigger picture. And then so the gigantic muck pile. Yeah, so I think I don't know if there's any consensus yet at the organization, the foundation, exactly what the future of that looks like. Right now we are under OSHA, not MSHA. If we start to do things commercial in nature with the muck pile, that might change. And I don't know if we want that to happen, but it's not like it's going to disappear. It's still something, you're right, we have, and there are different opportunities. The thing that, I don't know, the crazy idea that's been running through my head lately, especially with moving more towards dimensional stone industry tools, and in conjunction with this very large tower crane that we're getting, is we might be able to start pulling off a lot more like really large, nice blocks of rock and setting those aside. And what exactly we end up doing with those, I'm not sure, but I do know when you look at this big long-term vision, the mountain is the smallest thing in many ways. There's a beautiful museum complex, there's a university, medical training center, and those need to be housed in buildings. I don't know what would be more fitting than if important parts of them were constructed with pieces of the mountain. So I think there's probably a lot of creative ways where into the future, the mountain continues to be part of the foundation in perhaps expected and unexpected ways. Yeah, finally, sorry. Yes, sir. What's the next? What's the next? So this very large tower crane is going back behind the arm. And so immediate focus is, let's try to carve as much of that on the backside. This is not fun for visitors. It's like the side that no one sees, but let's get as much of that arm done as we can. So we can put that tower crane as close as possible to the arm. Then you maximize how much you can reach out in front of the horse's head, the horse's hoof. You'll actually, this crane, sorry, I'm in love with this crane. It's got at the end of the jib, your hook is 267 feet from the center of your tower, and it can lift 25,000 pounds at that range. It will clear the crazy horse's head by 47 feet, the hook height, and you'll be able to put something 500 feet down at the bottom, at the base of the mountain. You'll be able to reach out to the horse's head, back to Crazy Horse's elbow. So essentially the entirety of the carving, other than the tablet on the back, is within reach. So we're excited to get the pad ready for that, get that ready to go sooner rather than later so we can start to make the most of it. Otherwise, the tower crane, if it works as well as we hope it will work and solves a lot of these issues with access, moving equipment, moving rock, even moving crew, we've been sort of keeping this arm, this road access up on top of the arm because we place cranes up there all the time to move things around. But if you've got a big crane permanently back behind that, maybe we look at, I think it'd be just amazing to connect the hand back to the face via the arm. So again, that's my own opinion. No, there's no consensus on this yet, but that's one possibility. We're also starting to get to a lot of horse's mane. The thing with the horse's mane is like you got about 10,000 square feet between the face and the hand and parts of the arm. We've got about 32,000 square feet of mane to finish, and we really want to make sure we choose the right technique with that. So to get to the horse's head, we know we've got this big, massive amount of mane to finish. So there could be something with the horse's head, but that looks a little more challenging than the arm.
Does the training arrive?
Well, they tell me it can be here this spring, and then as soon as we have the pad ready, then we can put it up. So very soon. Yes, sir.
I sort of recall the scale model.
Yep. That should materialize someday. This is one of, since it's an additive process, one of the interesting things is, well, we might start with a 1/25th scale, no, a 1/4 scale feather, try out some different techniques, see what that looks like. And then you could imagine making the full scale feather and having it set down below somewhere where people can just see the size of it. And when you're ready to move it up top, you could. I don't know if your question was crane related. You could probably put that feather up in pieces with that big crane, or else you could put a spider crane up on top of the head to then put the pieces all the way at the top. What good questions? Yeah, way in the back.
What kind of attachment on the end are you planning? Saw or a carbide grinder?
Yeah, so our integrator's coming out and we're gonna have a long discussion. I think they said in the granite space that they've worked in, they have something like 24 different attachments they've been using. They were talking about a complete like mill garage on the frame. So we haven't fully homed in on that. If we can even just use some sort of blade like we've been using with the diamond blades, like even that alone will be a huge, I think a huge gain in terms of what we're doing. But hopefully by the end of October, I'll have a better answer for you. Yes, sir.
How many people are working on the project?
Yeah, that's like the trickiest question. I guess it's not that tricky. I just always act like it's a big deal. We've got, so obviously, I think you could tell there's a lot of support that goes into the guys actually running a drill, running a saw. On typical days in the winter, you're looking at about 6. Summertime, we bump up to maybe 9 of them. We've got people like Jim McNulty are doing important things in terms of IT support, also in terms of CAD work and rock support, a whole host of things. Plus, we've got some engineering consultants that work on specific projects. We've got me just like wandering around doing nothing much of anything. And you probably, between people also working on sort of the archival record keeping side of things, we're probably at about 18 people in the summer, maybe more like 14 in the wintertime. Surveyors, we have so much demand for surveying. We're just running the surveyors ragged at this point. Right. Well, speak now or forever hold your silence. Well, thank you so much again. Really appreciate it.
Thank you for coming, everybody. I just wanted to tell you quick about next month. So we do this every third Tuesday. Next month, that date is October 17th at 6 p.m. And we're going to have students who are working with the National Security Innovation Network at Mines. 2 students talk about a project they did recently, working with 2 other students from other universities on how to apply machine learning to address critical mineral supply challenges. So that should be pretty interesting. We hope to see you next month.
Hi.
This is Mark Anderson.
Hi, Mark. Nice to meet you.
Carla.
Hi, Carla. So nice to meet you. Oh, nice.